Okay, so let's continue. I mean, there is the discussions that we are having is not actually the current state of the affairs, but mainly how the modern physics developed. And we are more or less following their footsteps. What was the problem? What was the resolution? Which had a different problem, which created a different problem, what was the resolution, etc. But, I mean, we are changing so radically our understanding of nature that still one question still remains. You see, classical physics works. In our everyday life, we don't see most of the things that we see. We can understand them using just Newton's dynamics and classical Maxwell's equations. Where on some extremes, like at the atomic size, classical physics just fails so badly. So somehow, how can we explain with a single paradigm all these scales? I mean, how come something that doesn't work at the atomic scale, when you increase the size, starts to work? Or if quantum mechanics works at the even very small, at the atomic scale, how come when we get to larger scales, it coincides with the classical physics, so that classical physics works? So this is a partial answer is given by the correspondence principle. Which is in fact just a statement that at large scales, quantum physics, the predictions of quantum physics and the predictions of classical physics should coincide. You see, in the case of the hydrogen atom, the large scale essentially means large n. So because remember, the radius of the electron's orbit is given by the Bohr radius multiplied by n squared. So if n is large enough, you can have macroscopic atoms of the size of 0.1 millimeter. And in fact, we do create such atoms. So they are almost at the millimeter size, making sure that n is huge. So let's look at the emission problem, both from the classical electromagnetism perspective and from the perspective of quantum physics. So classically, this was the electron moving at a speed v. And classical physics predicts that it should emit electromagnetic radiation whose frequency is an integer multiple of the frequency of this orbit. So if the frequency of rotation is, let's say, 10 hertz, the emitted radiation should be 10 hertz. Now, what is this frequency? Well, this is just 2 pi r over t. What is t? No, 2 pi r over, sorry, it's 1 over t. T is 2 pi r over v. So frequency is v over 2 pi r. Now let's just put in the numbers for the speed and the radius of the electron that Bohr's model predicts. This is the radius. And we had also solved for the speed of the electron in terms of the radius. So the frequency was, let's replace v, this is n times h bar over m times r divided by 2 pi r, which is n h bar over 2 pi m r multiplied by 1 over r squared which is z e squared m over 4 pi epsilon 0 h squared times n squared. Did I miss anything? Hmm? Now here there's no r. And h bar over 2 pi m. So I have 1 over r squared. This is 1 over r. Square of this. So these are the frequencies. So nu should be the frequency of classical Maxwell theory predicts that the emitted radiation should be a multiple of this frequency, which is 1 over n cubed h bar over 2 pi m z e squared m over 4 pi epsilon 0 h bar squared squared. Now let's look at E1. What was E1? This was our E1. So nu is equal to well, there's 1 over n cubed. Now, let's see, if you look at E1, we already have z e squared over 4 pi epsilon 0, all of this squared. That is also over there. So I will just put E1. Now, what are the other factors? Well, let's see. I have that m squared divided by m. That m is already there with the correct factor. There I have 1 over h to the 4 from here, h squared, 1 over h to cubed over there. So here I have just an h squared. So I should have, let's see, divided by h bar. Let's count the factors of pi's. Let's see, over there I have pi cubed in nu. Here I only have a pi squared, right? There's a pi squared, so I should add another factor of pi. Let's look at factors of 2. There I have 16 times 2, 32. Here I have just 16, so I have 2. And I think that's it. This one. Yes, there is a 2. 16. Oh, yeah, you're right. There's no 2. Well, let's just write it. Well, this is, of course, there's a minus sign over here. So this is minus, or absolute value of E1, divided to absolute value of E1 divided by h, 1 over n cubed, or h nu is equal to E1, 2 over n cubed. So if classical physics, classical Maxwell theory is correct, this should be the frequency of the emitted photon, not just 1 over n squared minus 1 over n final squared. Now let's compare this with the quantum mechanical result. And the quantum mechanical result told us that h nu should be E1 times 1 over n initial squared minus 1 over n final squared. Now, the correspondence principle basically tells us how quantum mechanical effects makes a transition to the classical effects. That is, how if you are changing the size of your system, how one description kind of gets transform to the other description. And this happens for large systems, large quantum numbers. So in Ni, this should happen for Ni and Nf much, much larger than 1. So I will make an assumption. I will say, let's just say the initial state is N, which is much larger than 1. Well, not really an assumption. The final state, the final state is N, which is much larger than 1. And the initial state is, let's say, some p states above the final state. So the electron starts from a very high excited state, goes down to a very high excited state, and it just crosses p states. So the electron doesn't go to the ground state, because then the correspondence principle wouldn't hold. It just starts from a very excited state, makes a transition to another very excited state. And the difference, it just emits as a photon. Let's say it starts from the 500th excited state, and then makes a transition to the state with the quantum number 495. Then this N is 495, and this P is just 5. That's what I'm looking for. Now let's look at the frequency. H nu is equal to E1, 1 over N plus P squared. So this is final initial, sorry. 1 over N squared minus 1 over N plus P squared, E1, N plus P squared minus N squared divided by N squared N plus P squared. And I repeat, P is also much smaller than N. N is huge. Well, let me just simplify this a bit. H nu is equal to E1, 2NP plus P squared divided by N squared N plus P squared. Now I repeat, P is something around 1. 1, 2, 3, 5, maybe 10. N is a huge number, 500, 1,000, 10,000. So if you just look at this one, this number over here, this is like, let's say, 10,000 times 1. This is just 1. I can just ignore this one. This is 10,000. This is 1. Again, I can just ignore that one. So H nu will be approximately E1 times 2NP divided by N to the 4, which is E1 times 2 over N cubed multiplied by P. This is essentially the predictions of the quantum mechanics for states that are very, very excited. This is quantum physics. This is classical physics. And you see they are the same.
What was the different assumption we did when we derived classical physics formula?
Well, you see, this classical physics formula just says that accelerated charges emit radiation. And the frequency of the emitted radiation is some multiple of the frequency of the acceleration. So that's what we did over here. Of course, to calculate the acceleration, we need to use the radius. The radius we just took from the Bohr's model to be able to compare these two expressions. So we converted into this one. And in fact, since n is a huge number, just changing it by 1 or 2 doesn't really change 1 over n cubed. It just changes 1 over n cubed by a very small amount. So nu can essentially take continuous values if n is huge. But that is also what the classical physics predicts. Well, sorry, what quantum physics predicts. This is the prediction of quantum physics. If n is huge, any frequency can be emitted. It will be almost a continuum. Furthermore, the emitted frequency is an integer multiple of the frequency of rotation of the electron, just as predicted by classical physics. So this correspondence principle basically helps us to understand why classical physics works. Because when we look around us, what we see are objects that have very large quantum numbers. That is what we can see. We cannot see a single atom in the ground state. But if we excite a single atom to a very high state, then we can still see that. But then it behaves like a classical system, not a quantum mechanical system. So all these discreteness and the wave nature, it just kind of disappears. So, and that makes it difficult to directly observe this wave nature, wave phenomena, or these discretized orbits.
Is the factor in quantum physics expression, even though it is small compared to M, why does it make a difference when we compare to the classical model?
I didn't understand the question.
We have on the quantum physics model an additional factor of P.
No, classical physics tells us that the emitted radiation should be a multiple of this frequency. Well, the same thing. That's nothing but a multiple of this frequency.
Hocam, klasik fizikte bir atomun çok büyümesinden çok büyük kocaman ölçekte ulaşmasından çok bir sürü atomun birleşip klasik davranması gibi bir
That, well, you see, this is one, let's say, intuitive argument, the correspondence principle. The quantum mechanical predictions should make a transition to the classical predictions for large quantum numbers. Now, how does our classical world arise from quantum physics? Well, that's not so clear. I mean, you see, when you study quantum physics or quantum mechanics, you will be discussing about measurements. We don't yet understand what is measurement. Statistically speaking, if we just make thousands of experiments with thousands of atoms or thousands of electrons, quantum mechanics gives us the distribution, and our predictions gives us, our measurements gives us the same distributions. So there's no question there, but what is actually going on for a single measurement? That is still open to debate.
Hocam kuantum fiziğinin olasılıkçı yapısından mı geliyor? Yani
Yeah, that is not something we don't like.
Bunu deterministik bir şekilde çevirmeye mi çalışıyoruz? Yani ne bileyim, seçim teoremi olsun.
Not really. I don't know. I mean, even you say string theory and all kinds of other particle physics theories, they are quantum theories. They are all probabilistic. So what does it mean? So we would have been, as scientists, we would have been happy to get rid of that probabilistic nature, but at least the tests show us that we won't be able to do that. Well, there are some claim that the outcomes are determined by how your measuring apparatus interacts with what you are actually measuring. So we don't know. Gravity might play an important role there. We don't know yet. Yeah, any other questions? And this discovery of the levels of the atoms actually led us to the discovery of the lasers. Well, I will just give a short overview of how the lasers work. So You see, we have all these levels, energy levels. And although Bohr's model doesn't allow us to calculate the energy levels of multi-electron atoms, even in multi-electron atoms, even in molecules, we observe these levels. So we know that the energy levels of those systems are also quantized. And when if you send, let's say these three levels, this is E1, E2, E3, the processes that we can think of is stimulated absorption, which means that if you send a photon with an energy equal to this difference, E3 minus E1, and the electron sitting over here may go up to the third excited state. Or if you send a photon whose energy is equal to this gap, it can just go over there. Or if you already have an electron over here, and you send a photon whose energy is equal to this gap, it can make a jump to the third excited state. Then we have spontaneous emission. So let's assume that you send a photon, which is absorbed by an electron at this energy level, and it is excited to to this state. But it doesn't stay there indefinitely. Sooner or later, it just emits a photon and then goes to the ground state, or it can go to this E2 state. That is what's called the spontaneous emission. So let's say you have these three states. If you have an electron over here, it can emit a photon, and it can just go to this state, for example. This is spontaneous emission. Then the third possibility is what is called stimulated emission. This is actually what makes the lasers possible. Let's just consider this system. E1, E2, E3. You send a photon with energy E2 minus E1, and there is already an electron at the level E2. So with this photon, if there was an electron at the level E1, it could absorb this photon and go to the level E2. But there's no electron over there, let's say. There's only an electron at the level E2. So this atom cannot absorb this photon. The photon will not be absorbed because it doesn't match any one of these gaps, assuming this gap is different than this one. But what will happen is this electron can go down and emit a second photon whose energy is exactly equal to this one. And furthermore, it's not just its energy exactly equal to that one, it is also in phase. Yes, if you consider this light from the projector. Let's say here. To that spot, it emits some blue light. There are photons coming here with blue frequency, or an electromagnetic radiation coming there with corresponding to that blue frequency. But being a wave, not all the photons have their peak values at the same time or the minimum values at the same time. The maximum of one photon comes, and at that time, another photon that arrives is not at the maximum, but at a slightly lower value. Another photon will have minus the amplitude, etc. All those things add up incoherently, as they are not always positive, and give the final result. But in the case of the laser photons, these stimulated the photons created by this stimulated emission, they are always in phase. If one of the waves is at a maximum, the other wave is also at a maximum. If one of the waves is at a minimum, the other wave is also at a minimum. And in fact, this is what gives and they will be in the same direction also. So in fact, this is what gives the properties of the laser light.
So they are coherent.
They are coherent. They are pointing in the same direction. They don't diverge significantly. They will diverge by a very small amount.
What are the main reasons that make them coherent?
This is this stimulated emission. So essentially what it amounts to is that, let's say, if you have 10 photons, you already have 10 photons in your system. They are coherent. They have the same frequency. The probability of the emission of an additional photon coherent with the already existing 10 is enhanced by tenfold. So of course, I mean, since we are always talking about probabilities, this can also emit another photon which is not coherent with the existing photons. It's also possible by spontaneous emission. But the probability of this stimulated emission is enhanced by the number of existing protons, existing photons. New. Yes, one of them is already the existing one. That is the new one. Now, you see, in the spontaneous emission, you don't need anything. The excited electron just gives the photon. Gets de-excited. In the stimulated emission, well, in both of them, the initial electron is excited. It should have a high energy so that it can lose some of that energy in terms of photons. So we are at a high energy state. It can just go down, emitting a photon. That is spontaneous. Or it can also emit the photon due to another photon. There are already existing photons in my system, and the energies should match. If the energies match, then when the excited photon gets de-excited, there is a much larger probability for this new photon to be coherent with the existing photons. That probability is much larger. Well, you see, if there is an excited electron, then it can, if there is an excited electron and if there are existing photons in my system with matching energies, then I can have this stimulated emission phenomenon. The new one will also be coherent. Now then okay, so these are the basic principles. But still, how can we actually make the laser?
I have a question about if we de-excite the electron once, like we're sending a photon by photon, exciting and getting two photons first time, then we have an excitement level at 1, then next time we send the photon, it will absorb and send no photons. And will that go in the end, we don't have extra.
What do you mean extra?
Well, we don't have.
We don't have lasing. There are no lasers in that case. And just imagine, you just send a photon, one photon, you excite the electron, the photon doesn't exist anymore. Then the electron gets de-excited. Furthermore, the photon it emits can go in any direction. So you send one photon in this direction, at the end you obtain one photon moving in that direction, let's say. And then you send another photon, one photon, it might get excited. And when it's de-excited, it will emit a photon of the same energy, but in some other direction, most probably. So you don't get any lasers. But the idea over here is you send 10 photons having matching the frequency. The electron is already excited. If the electron is already excited, then when it is de-excited, when it's emitting the photon, it will most probably emit a photon in the same direction as the exciting photons and in phase with them. That is the idea of this stimulated emission.
So the electron absorbs the photon. Photon has a momentum. What happens to that momentum?
Well, I mean, you can of course think of this. We are not really thinking of single atoms. So you can have a crystal, for example. You can talk about crystals, or you can say a gas, but the photon momentum will be very small, and the mass of the atom is huge. So its velocity will change very slightly when it absorbs it. Now, of course, this is not how the lasers actually work. These are the basic principles which makes the laser possible. So what you do? You take some atom which has these 3 levels, but you cannot use any 3 levels. So this is unstable. This is what's called a metastable. What it means to be metastable is we didn't discuss much about spontaneous emission, but it takes us some time, typically 10 to the power minus 10 seconds. So if you have an excited electron, within a time of 10 to the power minus 10 seconds, typically it will emit a photon, almost instantly. But there are certain states that are called metastable that live, for some reason, a very long amount of time. For example, chromium, if I'm not wrong, it has such a metastable state. So the E3 state decays in a time of 10 to the power minus 10. The photon, the electron, comes into this metastable state, which lives 10 to the power minus 3 seconds, 7 orders of magnitude larger. So that is almost infinite, indefinitely.
Coherence of time number suggests.
No, it's not the coherence time. It's the lifetime of an excited state. How long does an electron in an excited state stay in that state before emitting a photon? So what you do? You take your material, for example, in this simple 3-level lasers, you have all these 3 layers. So you first excite all the electrons, or a significant number of the electrons, to the state E3. That is what is called a population inversion. So you just excite all of them to E3. A significant number of them, well, they will decay almost instantaneously, but a significant number decays into E2. And there it stays for a long time. So for a long time, you have atoms or electrons in the state E3, E2. But then, well, randomly, one of them just emits a photon spontaneously.
The reason for it to stay there for a long time is coming from third state. Is it?
Now, the reason why that state is metastable depends on the chemical properties of the material.
Because we said it was like 8
7 orders of magnitude longer.
Shorter, right?
It lives 7 orders of magnitude longer, E2. That is almost indefinitely in the atomic scale of time. So then what you do? You just send photons by some means, or by some other means, you just excite all your atoms. They all go to the state E3. And almost instantaneously, they go down to E2. So you have many atoms, many electrons at the energy level E2. Then one of them spontaneously emits a photon. But as that photon is traveling inside your material, it will cause stimulated emission of the other atoms. So they build up. Furthermore, quite often you put mirrors here. This is a mirror. This is what's called a semi-mirror. Basically, if the intensity of light is below a given range value, it reflects it. When it goes above, the intensity goes above a range, it just emits the photons, lets the photons to go through. So your photons, which started from one of them, just one of them spontaneously emitting, the photons move, accumulating other coherent photons, and eventually you get the laser from the other end. And you get a bunch, many photons, many coherent photons pointing in the same direction.
Hocam, semi-mirror E3'ten E2'ye giderkenki fotonu da yansıtıyor mu geri?
I don't really care. Oh, this distance. L is usually chosen as half the wavelength. So you can create standing waves inside.
The coherence of this phase comes from this.
No, the coherence comes from the stimulated emission. When you have stimulated emission, you always have coherence. And this is mainly these mirrors are mainly used to increase the number of photons. You see, the stimulated emission enhances the emission of a coherent photon by a factor of the number of photons plus 1. If you have a single photon to start with, the enhancement is not that big. It's just twice more probable to emit a coherent photon than an incoherent photon. That's not a big enhancement. So the photon moves through. You don't get much photons in the first run. Then they are reflected, but now you have 5 photons, let's say. Each one will create, as it goes through your material, each one will typically create 5 more photons, so you get 25 of them. Then in the second run, you get 5 more, multiplied by 5, you get 125 photons. So as the photons are reflected between these mirrors, you get the number of photons becomes much larger.
What is the desired coherency determined?
What do you mean?
How can we know that, like the first photon that comes, that was the probability, and which frequency it will have?
Which frequency? Well, the frequency is already fixed by your material.
Or what's coherence?
You see, this energy difference fixes your frequency. So by choosing your material, you are choosing the frequency or the color of your laser.
So the coherence is only important between the photons themselves.
Yes.
Like it's not some value that we should determine.
No.
Doesn't matter.
Well, of course, you can talk about the partially coherent light sources. I mean, you see, the sunlight is completely incoherent. Laser light is completely coherent. You can talk about systems midway between the two.
William, how come the electrons that come from third state is not coherent, but the ones that come from second state is coherent?
You see, the problem is this one. Why do we have this metastable state? An electron goes to E3. Almost instantaneously it goes down. Well, there are no photons around.
No photons?
No photons around yet. Because it doesn't wait long enough. This waits a long time. During that time, a photon from somewhere else will arrive. That is why it has to be metastable. Completely stable is not something that you like. Completely unstable is also not something that you like. So you have to have a sufficiently long time interval in which a significant number of electrons are in this metastable state.
I think there are no photons to emit no other photons.
No other photons
It's
matching that
still
frequency.
emission, right? It's still doing an emission when it's going from 3 to 2.
Yes, it is making an emission.
So
But since that, you see, you have one atom over here, one atom over here. You will typically excite all of them at the same time. You will try to at least. Then both of them are de-excited to E2. But the photon from here didn't reach this one yet. So they are both spontaneous emissions. But these metastable states waits a long time. Well, not all of them wait a long time, but they can wait for a long time. Spontaneously, one of them can decide that it won't wait any longer, it just emits a photon. So there is now a photon. You see, this electron is now excited. And the photon has time to reach this electron. So now it is a stimulated emission. It's no longer a spontaneous emission. Of course, there are a couple of more things. I mean, you cannot make sure that all the electrons are at the excited state, and for practical reasons. But what you need is more than half should be in this metastable state, because otherwise, if you have a significant number of them already in the ground state, when you have these photons, they will excite the ground state electrons to the E2. You will be losing photons. So you actually, that's in fact why it's called the population inversion. The population of electrons should be inverted from E1 to E2. A significant number of them should be in E2, not in the ground state.
So, do lasers emit in packets and in a continuous manner so that?
Well, this is one kind of laser. We have many different kinds of lasers. And, well, I think it's ruby lasers, for example. They use these ruby crystals as their lasing material. They just emit lasers in pulses. You get one laser beam, another beam, another beam. They are not continuous. But then you have other lasers like the neon nitrogen lasers, I think. I'm not so sure. They can emit continuous laser beam. They are a gas, because you can constantly pump the electrons from here to the metastable state. And there are the LED lasers, like those ones in the pointers. They don't work like this. They have a different working mechanism. But essentially, the idea is all of them use what's called this stimulated emission. How you create that system is a different we have different means of using that stimulated emission. Okay, so see you on Monday.